Hi, my name is Katherine Atkins,
And my name is Christine Pham.
and we'll be presenting over base flow and storm-based water quality from observations to urban stream imagery analysis. Our research is a preliminary study to analyze base flow and storm-based samples from a highly altered urban stream for various substances, including nitrate, iron, phosphorus, total organic carbon, tannin, lignin, and turbidity, to ultimately train a machine learning model and evaluate solute and contaminant transport from a high-resolution stream imagery. This type of study can help determine not only how precipitation events impact urban environments, but can also indicate the source and variation of substance concentrations. By the end of this study, we'll know the dominant concentration discharge patterns in a highly altered urban stream, whether it's dilution, chemostasis, or mobilization. We'll also be able to see and better understand the main drivers controlling solute and contaminant transport in a highly altered urban stream. Our study site is Rush Creek, which is located in the DFW Metroplex, the fourth largest metropolitan area in the United States. The area surrounding Rush Creek is mainly residential use and surrounded by urban infrastructure. The picture next to the map is a picture of our sampling location where you can see our sampling gauge.
For our methods, we started by collecting base flow and storm-based water samples. Then we prepared and digested the samples and used the colorimeter to quantify the measurements. Base flow is water derived from a water source when there is no input from precipitation, and storm-based water is derived when there is precipitation. We also took discharge measurements and images of the stream. The DIB200 was used to prepare our TOC samples by heating it up, and the colorimeter was used to measure the concentration of each sample by measuring the absorbance of light waves. As we get closer to obtaining a more robust data set, we plan to use the GRIME software to quantify watercolor values and use those outputs in our machine learning model. In the image below, we have our standards, which we use to regulate the calibration curve to make sure that our tests were accurate. Further down, we have some examples of concentration versus discharge graphs and what they mean. For dilution, concentration is inversely related to discharge, so as precipitation event starts to decrease, we expect the concentration to increase. Mobilization is the opposite. Both variables are directly related, meaning that if precipitation decreases, so does concentration. And lastly, chemostasis is similar to the concept of homeostasis in that the concentration will remain the same regardless of discharge increasing or decreasing.
For our results, we're first going to take a look at our hydrograph, which shows the change of water levels versus precipitation over time. The pink dot in this graph represents our sampling periods, and the highlighted section is the time period we'll be focusing on for this poster. The images below show what our sampling location looks like at various points of the hydrograph with base flow, rising limb, peak flow, and recession. The following graphs depict the concentration discharge patterns of the selected sampling period. From these, we can see that turbidity, total organic carbon, phosphate, and tannin lignin have a mobilization pattern as the concentration of these features are directly correlated to water levels, likely due to sediment transport into the catchment from urban runoff. Then we can see that nitrate and iron are characterized by chemostasis and dilution patterns. The patterns of these features indicate that they have consistent sources and transport is not impacted by urban runoff. However, more samples should be analyzed in the future to reduce outliers and better determine these patterns.
In general, we found that close proximity to urban areas and convective events, which are precipitation events that are greater than 1 inch, triggered a significant stream response coupled with sediment, solute, and contamination transport. And to reiterate, we saw immobilization patterns for TOC, tannin lignin, phosphate and turbidity, and chemostasis and dilution patterns for nitrate and iron. So what are our next steps? Manually collecting samples and testing them is financially burdening and time-consuming. By coupling water quality data and stream imagery, we plan to train a machine learning model to predict water quality based on watercolor variations using HSV color scale, which stands for hue, saturation, and value. Future sampling will also improve this model and reduce the need to manually collect and test each sample for its chemical content. By being able to measure concentration and discharge remotely, efficiency would increase greatly, which is extremely important due to how fast our environment changes from our input and lack of sustainability efforts as a whole. Thank you so much for this opportunity.